So we see in this video to create the bridge with OBM and after to transfer it to RM. So we have an alignment which is mainly an arc and some slope on the profile, where we will first define the pier lines. So I defined the three spans at the same time, giving a skew value which is different on each pier line and taken directly from the file you sent. So for each pier line we define the value of the skew and also the span length, because the spans do not have the same length. This can also be adjusted afterward. Okay, now when we have defined this, now we will model the deck. And for that we import the profile, cross profile of the deck. So select it in MicroStation and add it in the library by just pasting the definition into the specific windows for creating the profile. So we paste here with Ctrl C, Ctrl V, and we readjust the attachment point to the center of the profile, or any point that it should be. I'm not sure this is the right point. And we import that in the library. We can do the same for the profile of the beam that you can see in the same window. So here, select the profile of the beam, copy it by Ctrl C, and go to the library of beams, create a new beam, give a name, and in the same way, in this specific window, we paste the beam profile. We will just add one line to define the center of the top of the profile, so we can move this profile to the working point to be located exactly at the middle, top middle of the beam. And then we can remove the line. Now we store this profile that we will be able to use for placing the beams. Now let's go back to our model and we can model the deck. So we choose the profiles that we just have defined. and indicate that the deck will run from the first pier line to the last pier line. And now we have a model of the concrete deck. We will then define the location of the beams. So first we start with the beam layout, starting from the first line to the last line. And we indicate for each span different values. So first we will define the edge distance between the left and the right. Be careful that on the right the edge distance must be negative. We can adjust precisely the distance in millimeters on both sides, and if it's different at the beginning of the beams and at the end of the beams, we can also give different values. We then define the number of beams that we will put on each span, and also, so here we say that the beams are straight by default, so they use a chord. They are separated on each pier, and we have an offset at the beginning and offset at the end. Be careful that the offset at the end is negative also, and that the end of the beam is skewed, so will be parallel to the pier or the abutment on which they rest. And we do the same thing for the different span. Here I just took the values from the model of the bridge, so that's why we have different values for each span. But we have the same 7 beams on each span. Finally, adjust the offset at the beginning and the end of the beam again. Indicate that we have skew ends. And we can validate to see if this is exactly what we want. So we have straight beams on each span with a break on each support. So we can finally save this. Now the only thing we have to do is to attach the beam cross section to these different lines. So we will say that we use the same cross section for all the different beams. So that's why we have checked apply to all. We choose the cross section that we just have defined, and now it's creating the different beams. And we can review in 3D that is exactly what we want. We can then put the different supports. So mainly what we have to take care is that when we place the pier, we check the integral check. So the top of the pier will be part of the bridge itself, and we can address it on both pier lines. We will see afterward the different parameters for these different piers. We can have this pier to adjust themselves automatically to the width of the deck, but as we have different skew, the cap is adjusted automatically, but the wall is not. That's why I have two different piers adjusting by hand the width of the wall supporting the cap. In the same way, also, I have defined an abutment which looks like the one from the model I was given, but which is not exactly the same, and we will see how we handle this afterward. So here we have placed the different supports. We can review now in the library which are the parameters that I put for these different supports. So for example, for the pier, this way is quite easy because we have a very similar pier in the library, so we just have to define the different size of the cap and of the wall supporting the cap, then the number of piles and the general arrangement of the piles on the footing. For the abutment, it's a little more complex because there's much more detail than the one we can set up inside the parametric. So we mainly take something which is similar in volume. So we can handle this, for example, in the calculation. If we have a dynamic calculation, we will get approximately the same mass, but we don't have the same detail as we want, and we will see how we can continue with such things. So this is the beam. And finally, also, we have the possibility to add wing walls. So we just have to add a new type of wing wall where we give the different parameters of the wing wall, which are exactly the same that are placed on the model I received. So now we can place the wing walls. So we place them in skew along the alignment after each abutment on each side. So parallel to the alignment. So now we have a full model with the wing walls and the deck and the beams and the support. So in the next phase now we will place the bearings with the problem that for the bearings, by default, the bearings are placed just under each beam, and we cannot, for example, define a diaphragm at the beginning and at the end where we will put reduced number of bearings. So let's do as it is. So it means that we will just place the bearings directly under each beam. So we define the size of the bearing seats. We define also the size of the bearing, so the size of the cylinder, at which distance it is from the back wall, and we place these bearings, and we can see that these bearings, each bearing is placed under each beam, but at the same time it will give also the true dimensions for the abutment, especially for the height of the back wall. So we have finished our structural model here. We can continue with some details. So for example, we have on each side a parapet wall, for example. So I can place this using placing accessories, what we call accessories. So these accessories is just cells. So to be quick, I've just recopied the cells from new model, but I could have generated this model because it's just extrusion with a profile. But each parapet is a cell, and I have different possibilities to place this parapet along the side by referencing the point of attachment on the cross section, and either the number of cells I want or the distance between. So for example, when I have a transition between a small parapet and a big parapet, I just place one by one. Otherwise, when I have several placed at 3 meters from each other, I can place them like that one by one and continue directly where I want to place them on each side. So each time I define my point of attachment and placing the cell one after each other. So again, a parapet for transition, and finally the last one, with specific one for the end because it's not the usual length. So I have here I just took the one from your model and placed them, but otherwise I should have placed a standard one. See at which dimension I have to cut it with the skew effect. Modify the last one by cutting it, and I have to put it back in the cell library and place it with OBM so it is recorded by OBM for the quantities. I do the same on the other side. The main difference is that we place the same cell but with 180-degree rotation, and also we change the point of attachment, which is no more P5 but P1 in this case. But we can, in the same way, place the different parapets. This is surely the longest part of the modeling, and we have to modify this to make it simpler. Especially, we will be able to place all the cells at the same time and change one by one the different cells. Anyway, now we have finished, and we transfer this to our OpenBridge. So all this can be transferred except the parapets and the wing walls, which are not part of the same structure, but all the modeling and the numbering is done automatically. So the model is quite large because we have different cross-section. So it will create a grillage model of the bridge. Each beam is transferred as a composite beam with a precast part, which is the beam by itself, and a part of the deck, which is taken inside the composite beam. The abutment also is made. So if we look at the cross-section of a beam, typically you have the part 2, which is the precast beam, and the part 1, which is the cast in place part of the deck, creating a composite cross-section. And we have a grillage beam perpendicular to that, reflecting the deck structure as a grillage. So here we have in RM to add the diaphragms at the beginning and at the end. So here we just review. You see we have quite a complex model, but that can be used totally for seismic analysis, for example, where we have all the different piles and all the different things. We will have to set up manually for sure the stiffness, for example, the soil interaction between the piles and the ground. But we will have to do some modification on the structure to take into account the diaphragms and also the new position of the bearing. Here is our model, structural model seen in 3D, so the equivalent. So you see the abutment is not the abutment that we have in the reality, and we don't have the diaphragm beam at the beginning and at the end. So in order to place this diaphragm beam, we will go back to the definition of the abutment inside RM. So everything has been transferred both in modeler and in analysis. We will go in modeler and copy the cross-section of the abutment to modify it. So I create a new abutment cross-section, giving a new name, so abut 1 instead of abutment 1, for example, with the beam. And here I will add new construction line where I should put the diaphragm. The diaphragm is parallel to the abutment, so it's much easier to define it directly with the abutment. We give a different part, so it will be separated from the beam representing the abutment, but it will geometrically be placed parallel to the abutment, which is exactly what we have on the model. So I copy the two construction lines to indicate the size of the beam. Then I copy an horizontal line to indicate the bottom of the beam representing the diaphragm. Then I will indicate with a vertical line where I want my origin to be. The way I have defined the origin is that we will have after coincidental nodes between these diaphragms and the beam. So that means that I have to indicate exactly roughly the same position as the end of the beam, so the node representing the end of each beam. So I measure that on the model and I copy it here and put the origin of the new part. So create a new part, which will be 2. And define geometrically the cross-section of the diaphragm. So now my cross-section is complete, and I just have to replace it in my model. So I go in the abutment definition, and in the abutment definition I replace the old abutment 1 cross-section by abutment beam. So we have 2 sections attached in each node, and I replace this for all, and we see that there is a new line in the bottom appearing, which is our diaphragm, where I have to number it. So I just check which number are not used. Anyway, usually in all automatic model, it starts at 101. So we have some free space for numbering between 1 and 100, and we will benefit from that to do it. Didn't use it, so correct it. Okay, so I will put 11 and 12 here. Note by the material I have made a mistake because I use a default material in OBM, so it is transferred as material from H2 and not from Eurocode. So I should have modified this before I change it. So we can change it here or we can change it in OBM. The best is to change it in OBM to be sure that we transfer the good thing. So now we have numbered and we have a beam with the different nodes representing the diaphragm. And to make the connection with the beam, what we will say is that for each end of beam, we have a rigid connection between the node of the diaphragm and the end node of the beam, so that the diaphragm and the beams are rigid connected. What is a rigid connection is just that it puts only one node from which the beam starts, and this node is also part of the diaphragm beam. So this is a rigid connection, exactly what we have in our grillage model, for example. So I indicate for each beam what is the node I have to reattach. Note that this has automatically been cut at the proper place because we need, when we transfer, we had a connection representing the bearing under each beam. So that means that the beam representing the abutment has automatically been cut at the proper place under each beam. That's why we don't have to add new cross section. We just use the one that are there, and some are not used because they are due to some detail on the abutment and not from the beams. So we make the link between these diaphragm beams and each beam. To do this, I mainly read my model. So I have displayed my model on another view where I can read the equivalent node of the beam where I am on my model and the corresponding node on the abutment. So I can find the equivalent node on the diaphragm, which is quite easy to do. Note also that I'm using the segment 2 on my beams because the beam is shorter than the deck, and the first part of the composite beam, only the top part is present. So that's why I use my segment point 2 and not 1. And for the rigid connection, take care to make a rigid connection between the part 2, which is a diaphragm and not the abutment. So we have almost finished. And now we will define the last rigid connection between the H-beam and the diaphragm. So now I delete the springs representing the bearings under each beam because I don't need them anymore. And now I will add the new bearings, which are between the beams and the diaphragm. So for that, I will add new points, which are the exact location where I have these new bearings. For this, I will first indicate on my cross-section where I want to place my connection point. So from which point to which point is the bearing. So I take, for example, the middle of my diaphragm, and I attach my two connection points, one on the diaphragm and one of the abutment. So let's place this point at the intersection. So give a specific name I can find again. Spring 1 and spring 2 underneath. Okay, so running this cross-section again in my abutment. Now I insert the different segment points corresponding to the place where I want these bearings to be. So I indicate the first station of my bearing along the abutment, and the last one, and they are separated by 3.2 meters. So I can add these 4 points at the same time. So these 4 points are not numbered, so I will just renumber all the different things, so it will renumber at the same time. So the diaphragm, but also the abutment. So now I can place my connection between part 1 and part 2. So part 1 is my abutment, and part 2 is my diaphragm. So I indicate a spring representing the bearing. I will give a number, so I use from 11, so here I will use 1, 2, 3, 4, and I put the spring on one of the attachment points, whatever I want, where the spring will be represented. I can define the stiffness, so for example, let's put standard stiffness with only fixed in vertical and free in all other directions. And I do the same thing for the 3 other new bearings. My third bearing, with the proper stiffness again. And finally the last one. So I re-export my model by regenerating the model. Take the second thing to just be sure that we remove the deleted nodes, and it will automatically create the new nodes. And here we have the model, so we can check the model. If we see in 3D, it's not easy because there's a lot of things, so we can clearly see in the cross-section of the diaphragm running parallel to the abutment. And if we remove the display of the cross-section, so we see the cross-section of the beam looking like a box guider. Don't forget it's a composite beam. Okay, and if we remove the cross-section, so we will be able to see the springs representing the bearings between the diaphragm and the abutment. Let's take a clearer view, if it's possible. Okay, here we clearly see so the 4 bearings that we just added, and we can see So the abutment, the beam of the abutment, and the beam here. So now, if we want to continue the model, we can't continue with OBM, so you have to reopen the model inside microsession and use the solids that have been placed by OBM and modify this solid. So typically, for example, if we want to modify the abutment, we have seen that in the back of the abutment we have a specific shape. So I just have drawn this shape and cut the non-necessary part here that I removed. Okay, and also, for example, the back wall. So we have a part also which is different here. So we can just draw that part we have removed. So the easiest way is, after I have drawn the profile, is to create an extrusion of what I want to remove, and I do a subtraction between my original model and this. So you see, we put the detail also of the at the corner, the small arcs that we have, and I just remove that from my abutment here, and I remove this part. And finally, I got like that. So I can add many different details, but you can see that now I have the desired shape for my abutment. I can add more detail, or the ones that I'm not able to add. And also, as I'm in microsession, I can add all the attributes that I have to use for this. And this concludes how to do it.